So first of all, can we have BMT up to just talk through their bit, add the whole picture, and then we can talk through it later on. Thank you.
Well, thank you very much, everybody, for the opportunity to take 15 minutes of your time and talk about the assurance of autonomy. My introduction has mostly been done already. They've done a great job there of identifying the landscape we're working in. What I want to talk to you about now is how we assure MAS, so Marine Autonomous Surface Systems. And I want you to consider when we look at that, bearing in mind that I'm working in defence, that there's a very specific defence penalty for not achieving autonomy in a timely manner. Now, Andre's talked about the areas outside defence that autonomy can come in and touch. If we don't get this right, we will be the supermarine of the future. So we had the world's best product, we're no longer relevant. That's the thing you need to bear in mind when you look at autonomy. Not that I see a yellow box floating around the ocean now, it's what do I see in 30 years' time. So I'm Tom Howe, I'm the Head of Navigation and Seamanship at BMT, and for the last 8 years or so I've been working with the Naval Authority, who are the certifying body for MOD seamen, for BOD warships, in the assurance of autonomy. So much of the defence structure we've developed in concert with the civil servants at the NAG. With me today is my colleague Will Alexander, who's Deputy Team Leader of our autonomy section. BMT are a whole ship design house, as you will have seen as we've come up through presentations in the day. We're designing FSS, and we're also a technical consultancy. So what autonomy can be and how is something that really matters to us, because if we don't understand that and we can't build it in, we are the supermarine of the future. So understanding where this is now and what we do with it is life and death for us. And it is for a lot of people in this room, whether you recognise it now or not. So what are we going to talk about? I'm talking about a very specific part of what's been outlined here as a broad problem. Safe and effective MAS operation. And we're looking at the mariner-like decision-making within autonomy. And we're looking at that because that's the bit of autonomy that's different. 95% of it is core engineering that we do all the time and we understand and we can just go away and make work. The bit that's different is where the system needs to think like a mariner, and it needs to fit into that mariner thinking ecosystem in order to be operated safely. So what we're looking at is the problem of autonomous anti-collision. So when your MAS encounters another vessel in a way which engenders the risk of collision. We're looking at systems that are working with a human in the loop in some way, because those are the ones we're being asked to certify at the moment. And that realistically is where the boundary of technology is. We're looking at assurance. I'll introduce you to MAS-Cs, which is one of the 3 routes to certification in defence, using synthetic environment testing. And we'll talk about that in our Rembrandt simulator and how that's used in this area. So what is safe and effective operation? Well, you could say that safe and effective ops are those where a failure of the system is tolerable. So the application of the collision regulations going wrong is tolerable. There is an ISO technical specification which gives us a whole lexicon for autonomy, which came out last year and is an extremely powerful document, actually. Because as Andre's pointed out, the language is all over the place. If you can start getting people to understand one another when they're talking about a problem, picking that problem apart gets easier. And in that standard, the tolerable event is a technical or operational event for which there is a designed response that keeps the system within its operating envelope. Now, that's the last time I'm going to read out a bit of a standard, because I want to keep you with me as we go through this journey. But the important part of that is the bit at the end that says operational envelope. Because if you get your operational envelope right, the human has time to step in when the machine makes a mistake and can recover the system before the risk of collision manifests itself. So tolerability of failure is about understanding the capability of the system and defining an operating envelope. And that's what MAS-Cs does. It provides regulators with evidence that allows them to define the shape of that operating envelope. As I said, it's one of 3 routes to certification in defence. The first one is to operate your system on a clear range. The second one is a defined set of performance requirements, which at the moment are beyond the capabilities of any of the systems we've seen developed. And the third one is this. which is to take your system away and test it in a synthetic environment so we understand how appropriately it applies the collision regulations. It doesn't test repeatability, it just looks at how appropriate the decisions in the sample size of tests are. And actually, as an experienced assessor of people applying the collision regulations, you can pretty much nail the performance of a system in a week. We're taking this approach because we're dealing with immature technology. Now, that point of there is a clear risk to not having a timely implementation of autonomy in defence takes you straight to, how do I safely use immature technology when I have a third-party risk all around me? And that's the bit you've got to nail if you're going to maximise the operation of these systems. As we heard earlier, we've already got them in the Gulf. Getting the man out of the minefield is one of the long poles in the safety argument for autonomy. So actually, be able to push out systems which do that have an immediate and tangible benefit. And these systems are far more capable than the one which have 50 people in them. They do it quicker and better. So actually, you've got to solve the safety problem of how do I safely operate this system. What MAS-Cs does, and that's probably what you've all been sat there thinking, is simply takes the brain of the autonomous system, so the bit that's making the Mariner-like decisions, and it integrates it into a synthetic environment, so a bridge simulator in effect. And that allows you to test it in exactly the same way that you test a system, that you test a human. So MAS-Cs is based on the principle of equivalence in certification, which we use in defence certification in lots of different ways and areas. And what equivalence says is, I don't have a standard for this, but what do I have that looks about the same? And can I say it's as good as that? And the equivalent we're looking at is the human on the bridge, of course, and humans apply the collision regulations. Now, I expect everybody in the room's heard of the collision regulations, but your familiarity with them may vary. They're the rules used by mariners to avoid collision, and then subsequently by maritime courts to apportion blame if you have a collision. They are a subset of a broader duty for the observance of good seamanship, which is the thing you generally end up in court for when it's gone wrong. And they're a subset of that because they're the part of that duty the IMO could agree the wording to. So when you look at the coal regs, it's a fairly thin document that covers a fairly broad responsibility in language which is predominantly goal-based and hard to interpret. When you give that to somebody who develops software, what you get back may not be what you imagined, because they have an insurmountably difficult job from where they're sat. It takes years to understand the collision regulations, and it takes longer to write software. Putting those two skill sets together is perhaps something that we didn't do effectively at the beginning of the projects. So, the safe operation of MAS relies on an appropriate application of that broader duty for the observance of good seamanship and the collision regulations. And for immature systems, a failure to do this needs to be a tolerable event. So how do we establish that and hold that thought? Look at what we do with humans. Humans are certified by an appropriate authority, having demonstrated their competence in front of an independent third party. And that is done on a tailored scale. So we don't require everyone who drives a boat to be as good at this as everybody else. So at one end, you've got a powerboat level 2, and at the other end, you've got a master mariner. And a whole range of qualifications in between, depending on what it is you want to do, where and in which vessel. So the idea that we tailor our qualifications is not a new one. And sticking with the idea of equivalence, it gives us a powerful weapon. SEAS does the same thing. It looks at the technical capability of the system. Because if there are parts of the collision regulations this system can't do, if it doesn't recognise a narrow channel, there's no point testing that, and actually you can't let it operate there autonomously. So fairly rapidly, when you look at the thing they've put in front of you, you can go through and say, I don't need that bit, I don't need that bit. This is what we're testing. You can then look at the areas they want to operate in. So I'm not operating this anywhere busy. Fine, I don't need to test high densities of shipping. All of that tailoring gives you a test syllabus. You then take the MAS brain into the simulator, run it through the syllabus, assess its performance, and provide a report. That report's given to the regulator defines the operating envelope. So to quickly look through that, tailor your assessment for your vessel type and task. Test the machine's decision-making, analyse the results, highlight areas of strong and weak performance, and we don't talk about success and failure, because the coal regs are grey. So it might do some things quite well, and it might do some things quite weakly. And there might be some areas where you just have to say to the operator, in this situation, you will have to take control because the system will not resolve the problem. But once you know that, you can define your operating envelope. The certification is based on that defined operating envelope, which comes from an understanding of how the system applies the collision regulations. In a second, I'm going to hand over to Will, which is warning to get on the stage, to talk to you about what the synthetic environment does. But what this approach allows you to do is rapidly iterate through a series of spirals based on that assessment of the operating envelope. So when you look at the Colreg performance of the system, you can look at that and say, this is the bit that's constraining me. And you can say to the MAS developer, this is where your biggest problem is. And this bit, if you change here, gives you the biggest return. And they can go away and look at technically how you do that quickly. So change a piece of equipment, change a piece of software, change a process. Bring the system back, retest it, bigger envelope, quickly. And you keep doing that until the operating envelope doesn't stop you doing what you want to do, so it doesn't matter anymore, or you achieve a full release and you have software that's fully compliant. If you don't take an approach like this, you're stuck admiring the problem for years while you try and solve a global structure of how we're going to do this. So this approach is working now in defence, and it's allowing us to quickly get stuff regulated into the water and certified. Now, Will, do you want to talk through what the synthetic environments do?
Yeah. Thanks very much. For vessel owners, it accelerates the route to certification, enabling capabilities to enter service more quickly and move from design into productive operations much more quickly. And for the operators of these systems, it provides a safe environment to train, to demonstrate performance, and this builds confidence and trust, and ultimately feeds through to safe maritime operations. This approach that we've been discussing has been independently supported by existing research into safety assurance of automated systems in other domains. Its simulation is used successfully in land and air domains, and it's equally as applicable in the maritime domain. Recent research papers by Warwick that Andre's already alluded to, also University of York have been doing some work under their Assuring Autonomy International Programme, and also, again, Andre has alluded to with the MPL paper on the requirements for test environments for autonomous vessels. So there's independent research out there that supports this. However, as the quote from Warwick says there on the screen, having the virtual test environment gives you a huge range of advantages, as I've already outlined, but you must be able to ensure that the virtual environment itself reflects the real world as closely as possible. You must be able to trust the results of the tests within a given scenario. This is where BMT's Rembrandt comes into the equation. So very briefly then, what is Rembrandt? It's a system that's fully scalable, it's DMV type approved, and it's a synthetic environment. It's fully federated, it's easily networked with open architecture. It can be integrated with UKHO tidal bathymetric data sets and next generation S100 products. And when it's combined with BMT's 2Flow, world-leading hydraulic modeling tool, it can provide very high-resolution vessel hydrodynamics, making Rembrandt, the system as a whole, the most versatile and capable synthetic environment commercially available. It can be run in real time or with live real-world contacts, and it provides the opportunity to operate in concert with remote autonomous or remote control platforms and conventional assets. It can be standalone or support a wide range of activities. With appropriate sensor inputs as well, Rembrandt may be expanded to become actually a live digital twin. So it's been developed by BMT from scratch as an engineering tool, and it's a mature technology. It's used by many of the world's largest shipping companies, oil and gas companies, and statutory investigation bodies as well, like the UK MAIB, as well as other port operators. At BMT, we're exploiting the wider potential of this system with autonomy. for testing, evaluation, operational planning, mission rehearsal, as well as training. And Rembrandt provides a sufficiently realistic and accurate model of the real world to give you that confidence in the results. So I need to bring this back to the original question of how safe is safe enough. And really, this is bounded by the operating envelope, as Tom has set out. Understanding your vessel's system performance is key to building the evidence to support the definition of the safe operating envelope. It allows you to manage the risks and put the appropriate mitigations in place, and being able to tailor the operating envelope based on the performance and adapt it for specific circumstances, such as the mode of operation, the level of autonomy, the task, the geographical area, vessel size, etc. This allows you to prepare for live trials and real-world operations. So with respect to the autonomous system as a whole, and within the context of what Tom has already described as a tolerable event, the system can be considered to be safe enough if a failure to make a decision with due regard to the observance of good seamanship is made apparent to the human operator in ample time for them to intervene. So there is a human in the loop, but that human needs to be in a situation where they can take control. And for this to be the case, you need a clear understanding of the system performance and the defined safe operating envelope. So just to conclude then, just to reiterate those points, the synthetic environment allows the collision regulations performance of the system to be understood in a way which allows an appropriate operating envelope to be defined. And this means immature technology can be certified and operated with the minimum of constraint, and that will only help accelerate these autonomous systems into productive use. Just to leave you the final quote that I came across from the Nippon Foundation, this goal of half the ships in Japan being fully autonomous by 2040 is a real goal they have, and I think it gives us a glimpse into the future perhaps. And this is being driven by a shortage, or projected shortage, of suitably qualified and experienced mariners in the future. So they're very much looking for automated systems to step in and fill that void. So that's everything from me. Thank you for your time.